Hi, I am Alejandro Di Gumiso Jr., a 5th year student of Engineer Jamer Punsalan in Power Plant Engineering Laboratory. Today, we will talk about ocean thermal conversion. But first, let's see what we can learn today. Let's look for our objectives. The number one is what is ocean thermal energy? The second one is the brief history of ocean thermal energy. The third one is what are the major components of uh, ocean thermal energy. The fourth one is what are the principles and operation. Fifth, advantage and disadvantages. Six, what are the progress of ocean thermal energy in the present time. Okay, let's start. First, what is ocean thermal energy? According to Yamada et al. 2009, ocean thermal energy conversion or OTEC is a power generation method wherein the heat energy associated with the temperature difference between the warm water surface water and cold deep water of the ocean is converted into electricity. Ibig sabihin nito ay ang ating ocean ay may warm surface dahil sa init ng araw at deep cold portion. Yun yung nasa ilalim ng dagat. Kapag pala kinuha natin yung temperature difference nung dalawa, ay pwede natin itong i-convert into electricity. For us to learn more about ocean thermal energy, and now let's look to its background and history.
On 1881, proposed a closed cycle ocean thermal device by John Campbell, an American engineer and two Italians. Their principle is that the warm surface water would heat and cause evaporation of the working fluid, which would pass through a turbine, there being condensed by cold water pump up from deep layer and again fed into the evaporator. In 1931, open cycle system by George Claude, a French engineer. His 1 meter diameter turbine generated 60 kilowatt at 5,000 rounds per minute with a total ocean thermal difference of 20 degrees Celsius. His principle in which the ocean surface water itself evaporates and drives the turbine, the sea water itself. In 1951, the Seawater Conversion Laboratory founded by Professor Everett D. Ho. In 2013, Saga University, with various Japanese industries, completed the new installation of OTEC plant. And that's the brief history of ocean thermal energy conversion. And now, let's look for the major components of OTEC or the Ocean Thermal Energy Conversion. Dito, malalaman natin kung ano ang function ng mga components at normally kung saan sila nakabit. Let's start. The number one are the water pumps. We have 3 water pumps here. One is in the warm water pipe of the system. Second is in the cold pipe, and the third one is in the working liquid pipe of the system. Sa diagram, dito natin makita yung location ng tatlong pump. The second major components is the heat exchanger or the evaporator. It composes of two parts, the warm water part and the ammonia gallery part. In this section, the heat of the surface ocean evaporates the working fluid, which is the ammonia, into gas state. The third component is the heat exchanger condenser. It composes of two parts, the cold water part and the ammonia gallery part. Cold deep sea water returns the working fluid into liquid state. Sa drawing, makikita natin yung dalawang portion. The fourth major components is the turbine generator. The pressurized working fluid in gas state drives the turbine, and this rotation will drive the generator that will convert from mechanical to electrical energy. And one of the most important in the system is the working liquid or the ammonia. The popular choice of working fluid is the ammonia, which has superior transport properties, easy availability, and low cost. The good characteristic of ammonia is it is volatile. It means it is easily to evaporate at normal temperature. And now, let's go to the principles and operation of OTEC. The OTEC uses the warm surface water of the ocean with a temperature of around 25 degrees Celsius to vaporize the working fluid, which has a low boiling point, such as ammonia. The vapor expand and spin the turbines, coupled to a generator that produces electricity. The bigger the temperature difference, the higher the efficiency. For better understanding, let's see in the drawing. This is a sample of closed system cycle of OTEC. In this portion, ito ay ang condenser side. We have the pump. Of course, siya yung nagpa-pump ng cold water galing sa ilalim ng dagat, going to this container, which is the heat exchanger condenser unit. In addition, yung pipe dito ay meron siyang haba na at least 1,000 meters. Ang condenser ay para siyang shell and tube type na kung saan sa loob ay matatagpuan ang ammonia gallery or yung piping ng ammonia, at sa labas na portion niya ay yung daanan paloob at palabas ng warm water. In this portion naman, makita natin yung heat exchanger evaporator unit side. Same operation sa condenser side, pero ang tubig dito ay galing lamang sa mga mababaw na surface ng ocean, dahil para makuha yung heated part na tubig. And the next portion is the closed loop of the system. Dito, matatagpuan yung pump na nagpapaikot sa working fluid natin. From evaporator, gagawin niya in gaseous form yung ammonia, dahil na din sa temperature na nanggagaling sa warm ocean water. Sunod ay pupunta sa turbine. Because of the high temperature and high pressure, napapaikot ang turbine. At ang turbine ay may nakakabit na generator that convert the energy into electricity. Pagkatapos naman niya sa turbine, pupunta ang ammonia sa condenser side. At unti-unting babaguhin ng condenser ang ammonia at gagawin niya itong liquid form ulit. Dahil na din sa cold temperature, galing sa deep water ocean at paulit-ulit lang yung sequence ng operation.
And there you go. Ngayon, alam na natin kung paano yung operation ng OTEC, kung saan siya nagsisimula at saan siya natatapos. Ayan. So ngayon, let's go for the advantage and disadvantages of OTEC. The first advantage of OTEC is OTEC is a clean and it is renewable. Wala itong pollution na nilalabas. Wala itong nilalabas na usok. Hindi tulad ng mga ibang planta na makita natin sa mga upper part nila na merong mga nilalabas na usok. Pero sa OTEC, ito ay malinis. The second advantage is power developed is continuous and it is independent to weather. Kahit magkaroon ng bad weather ay continuous pa rin ang production ng energy nito. Pero syempre, alam natin na yung mga planta na bago pa ito itatayo ay nagkakaroon ng mga studies. Studies ng pagtatayo ang lugar. Kailangan mo nang ma-meet yung mga iba't ibang requirements dun sa area na yon at syempre marami ka rin dapat consider. The third advantage of OTEC is there is a small variation of power output from season to season. Ibig sabihin nito, meron lamang maliit na pagkakaiba sa power output kung ang panahon ay nagbabago-bago, kung tag-init or taglamig or tag-ulan. And the fourth advantage is it can produce simultaneously the desalinated water and nutrients for agriculture. Malaki ang naitutulong nito sa agrikultura. Ayun. So, kung merong mga advantage yung planta ng OTEC, so meron din naman itong hindi maitatago na mga disadvantages. Okay, let's go. The number one and obvious disadvantage of OTEC is the capital cost is very high. Ang mahal ng paggawa ng plantang ito. Sa size at length of pipe pa lang nagagamitin sa suction ng tubig, sa cold water pipe ay talagang tumataginting ang mahal ng presyo. Dahil hindi naman basta-bastang tubo ang ilulubog mo doon. Kailangan ma-meet pa rin nung pipe na ilulubog mo doon yung iba't ibang requirements. Halimbawa na dito yung alon at iba pa. At ang cost nung pipe, yun yung cold water pipe, according to my research, ay nasa around 15 to 20% of the total cost of the plant itself. At halimbawa na dito, yung cost lamang ng 50 megawatt, yun yung net power ng isang planta ay approximately nasa $70 million. At sabihin na lang natin na nasa 15% yung cost ng cold water pipe at ang tumataginting na price ng pipe ay $11.25 million. Kaya magastos talaga yung OTEC. The second disadvantage of OTEC is the cost of electric power generation per kilowatt is very high. Dahil nga hindi pa masyadong kilala ang ocean thermal energy conversion, ay may time na meron talagang mas mahal yung singil nila per kilowatt hour. The third disadvantage of OTEC is it takes a lot of energy to pump the cold water to the surface. Kung ang haba ng cold water pipe ay nasa at least 1,000 meter, ay kailangan mo rin syempre ng malaking pump para sa paghigop nito. So syempre kung malaking pump, malaki rin ang kuryente na nako-consume nito.
And now, let's look for the progress of ocean thermal energy in the present time.
Every day, the sun transmits millions of gigawatts of solar energy to the surface of the Earth. This is thousands of times more energy than all the power consumed daily by mankind. Much of this incoming solar energy is absorbed by the oceans, which act as a massive heat sink, a kind of enormous heat battery. Ocean Thermal Energy Conversion, or OTEC, a bold yet simple way to tap this heat and convert it into electricity without any additional fuel, has the potential to significantly reduce the global consumption of fossil fuels. The OTEC concept uses the temperature difference between warm surface seawater and the deeper cold water. In tropical waters, this temperature difference can be 20 degrees Celsius, about 36 degrees Fahrenheit or more. In this design, a semi-submersible platform is moored several miles offshore. The platform supports a kilometer-long pipe that conveys the cold seawater to the platform. Simultaneously, warm water enters the platform from the surface. The warm water passes through an evaporator which boils a liquid working fluid, such as anhydrous ammonia, contained within a closed circuit. The now gaseous ammonia drives a turbine to generate electricity. The gas then enters a condenser where it is cooled by frigid seawater from the cold water pipe, returns to a liquid, and is pumped back to the evaporator to continue the cycle. A Lockheed Martin Corporation-led team of subcontractors has designed a 100-megawatt OTEC system capable of fabricating the 1,000-meter cold water pipe, or CWP, directly from the platform. Once the cold water pipe is completed, the fabrication facility is removed and the power modules containing the seawater pumps and heat exchangers are installed. The United States Department of Energy and Lockheed Martin jointly sponsored model tests of the semi-submersible platform, the cold water pipe, and the connection between the two. These tests examined each of this marine structure's many configurations for motions, forces, and pipe bending behavior. The project's test data will be used to validate the numerical predictions of platform and pipe responses to operational and extreme waves. Testing at the relatively large scale of 50-to-1 was conducted at one of the few hydrodynamic research basins in the world that can accommodate such a deep model, Lab Oceano. Located near Rio de Janeiro on Ilha do Fundão, a sort of Silicon Valley of deepwater petroleum technology, this exceptional facility is operated by the Federal University of Rio de Janeiro. Nearby are the headquarters of Petrobras, the Brazilian oil company, and a host of the leading companies in the deepwater oil industry. The model test program at the Lab Oceano examined 3 of the major components of the OTEC system. Based on the proven semi-submersible design common to the offshore oil industry, the platform is well understood from decades of development and operations. The fiberglass-covered aluminum model is 1.4 meters square and 800 centimeters high, roughly 4.5 feet square by 2.5 feet high. The semi-submersible was tested in 4 configurations. The platform by itself, ballasted to include the weight of the pipe fabrication facility. The platform with 6 power modules. The platform in the cold water pipe fabrication phase without power modules, with 2 different pipe lengths of 500 and 1,000 meters. And the platform in the operational mode with 6 power modules and the 1,000-meter CWP. The total full-scale weight of an operational OTEC system and platform is 217,000 tons. The fiberglass reinforced cold water pipe has a full-scale diameter of 10 meters, which is 2 meters larger than one of the railway tunnels in the England to France channel. The total cold seawater flow rate is about a third that of Victoria Falls in Zimbabwe. Here, two technicians stand beside a 4-meter prototype model of the cold water pipe built by Lockheed. The mass of the cold water pipe, including the entrained seawater, is greater than the mass of the semi-submersible platform. The CWP is significantly larger than typical pipes used in the offshore industry, so determining the model's scale pipe's loads and the behavior of the coupled system are vital to assessing the entire project's feasibility. A previous investigation of large-diameter composite pipe was an extensive 1983 NOAA-sponsored at sea trial of a 2.5-meter diameter, 130-meter-long reinforced fiberglass composite pipe. These trials yielded important data about the pipe's behavior, bending characteristics, and fatigue life. The cold water pipe model has a core tube consisting of 4 sections of 38mm or 1.5-inch diameter aluminum pipe. This models the bending stiffness of the CWP. The outside diameter is modeled by 20 discontinuous tubular sheets made of composite material, which represents the pipe's hydrodynamic diameter. The outer sections are centered on the inner core, and adjacent sections are sealed with rubber strips so that bending stiffness is not affected. The pipe core is instrumented with 20 sensitive strain gauges. Here, 1/2 of the assembled pipe is suspended from the lab's rafters for a pipe impulse response test. The impulse is applied to the core with a common hammer to determine the natural frequencies of the pipe. The strain gauge data is displayed for each channel as a timeline. The pipe's spatial location is measured with an underwater optical tracking system. The CWP is floated into the water, and divers install the 20-meter model in the Lab Oceano test basin. The depth at the bottom of the center pit is 25 meters, deep enough that the divers must decompress before emerging. Because so little is known about the behavior of the cold water pipe in the physical world, the loads, motions, and bending test data is invaluable. During fabrication, the cold water pipe is almost rigidly connected to the platform. As the fabricated length becomes longer, the pipe's response to waves and currents increases and begins to affect the platform. Because there is no way to accommodate its motions relative to the platform, the coupled structure is particularly vulnerable to storms, with the largest loads and forces concentrated at the lower location. In operation, the CWP is coupled to the platform by a huge gimbal, which acts like a universal joint to accommodate the motions and lessen bending strains on the pipe. The model gimbal was carefully instrumented to record forces and angles. 2 different gimbals were tested, a free gimbal and a restrained gimbal. The ideal locations for OTEC systems are in tropical waters with 1,000-meter water depth within several kilometers of shore. Within the United States, Hawaii and Puerto Rico are of prime interest. Internationally, there are many candidates from the South Pacific to the South China Sea as far as the Indian Ocean. The wave conditions selected for the tests cover a range of likely design conditions for these locations, from monsoonal storms to large swells to tropical cyclones. The tests shown here were conducted on the coupled OTEC model in the operational stage with a free gimbal.
and that is ocean thermal energy conversion. Thank you for watching.